This lesson is 18A, which is area under a curve. And this whole chapter is on integration. So let's consider a function. So this will be example 1.
Summers Harpana, please come to the office.
Let's consider f of x equals x squared plus 1. And we want to estimate the area enclosed by the function, the x-axis, x equals 1 and x equals 4. So first let's sketch it. Okay, x squared plus 1, so that's going to go up 1 unit. It's a parabola opening up. And I'm not even going to get all that picky with how I graph it. So this is going to be x squared plus 1. And then here's the line x equals 1. Here's the line x equals 4. And we're interested in this area here enclosed by the x-axis and those 3 curves. And we also are so we're doing an estimate. What we're going to do is we're going to use rectangles to estimate the area because we don't have a geometric formula for that shape, that two-dimensional shape. And the problem is going to ask us, or we're going to use 3 subintervals. In other words, 3 rectangles. So there are 2 ways you can do your rectangles. Actually, there's actually 4 ways. Well, 3 ways you can do rectangles. But the IB is just doing the, they're calling them, what do they call them? Upper rectangles and lower rectangles. So we'll set it up using upper rectangles and then we'll set it up using lower rectangles. Okay, you can see that 3 subintervals would be dividing the x-axis like so into 3. And then if I want to use upper rectangles, that means that the rectangles are going to be larger than the region, upper being above. And so on my first rectangle from 1 to 2, if I want the rectangle to be above, I'm going to be using the right-hand side, because if I come across, maybe I'll do this in a different color. So that would form an upper rectangle. And then I'm going to also do the next one will be here, and then the next one will be here. So in the AP, we call that RAM. Just so you know, I mean, it's good for you guys to know some different notations. That's because it's on you use the right hand, like on the interval from 1 to 2, we used the 2 to get the height of our rectangle, and 2 is the right hand bound. And then RAM stands for rectangular approximation method. Okay, so now we're simply going to find the areas of each of those 3 rectangles. Notice that the widths are all 1 unit. So instead of multiplying length times or width times height plus width times height plus width times height, I'm going to pull out the width and factor it out to the front. So I've got a 1 because they all have a width of 1. And then to get the height of the first one, that will be dependent on using 2 as my x value. So I'm going to be plugging 2 into my function to get the y value. So 2 squared plus 1. And that'll be the height of the first rectangle. Then the height of the second rectangle has 3 will be the x, so it depends on the 3. 3 squared plus 1. And then the last one is 4 squared plus 1. So I'm plugging in the x's into f of x to get the height. So this is the height of the first rectangle, the second one, and the third one. And then it's just a matter of doing the math. And I've worked these out ahead of time, so that one happens to be 32 units squared. That's the upper rectangle method. And I'm trying to remember, oh yeah, the IB uses A sub U for upper area based on the upper rectangles. Now we'll change colors to red. and we will do the lower rectangles. So I will draw them in red. So for this first one, the lower rectangle, these are going to be under the curve. I will be using the left end point on each of my rectangles. So these red marks will be the heights of the lower ones. Here's the lower ones here. In AP we call that LRAM because we're using the left-hand side of the subinterval to determine the height. So again, the widths are all 1, so I'm going to have, so we can call this A sub L. The widths are all 1. We'll factor that out. And then the height of the first one is going to be, I'm going to have my x of 1. So I'm going to have 1 squared plus 1. The next one will be 2 squared plus 1. And the next one will be 3 squared plus 1. If you calculate that, you should get 17 units squared. So the real area, the actual area, is between those two estimates. So I could write over here, I could put area sub A for actual is going to be less than 32 and greater than 17. What would give us a better estimate? More rectangles, right? Okay, so now what we're going to do is what I would like you to do is try this on your own. Find the estimate using upper rectangles and lower rectangles for 6 subintervals and see what you get. So, and then I will also do it so you can check your work. Oh, that's not very good. Okay, I need to draw the picture again. What was this again? It was x squared plus 1. It doesn't need to be super perfect. And this time we're doing 6. Oh, I should have drawn it a little bigger. It just helps it helps to see these pictures. So the widths. Oh, well, yeah, you could figure the width out just by common sense. But there is a little formula that you can use. And so delta x is the width. It's going to be the upper bound of 4 minus the lower bound of 1 divided by how many subintervals you have, which in this case are 6. So 4 minus 1, 3, 6, so 1/2. That formula is written delta x equals b minus a over n, because you go from a to b, and then n is the number of subintervals. That little formula will come in handy later, so that's why I'm telling you about it now. Okay, so since you've had a chance to try this on your own, I'm just going to go ahead and write down the work, and then you can check your work. So a sub u, the upper rectangles, that'll be these. They're going to be based on the right-hand side of each interval. So the first one's going to be 1.5. Oh, and my width, I forgot, got to do the width out front, so that's 1/2. Okay, 1/2 out front, and then 1.5 squared plus 1 plus, and then 2 squared plus 1 plus 2.5 squared plus 1 plus 3 squared plus 1 plus 3.5 squared plus 1. Now notice as you get going towards the end here, actually this one right here is 3.5. If I'm doing the upper ones, okay, this one, and you should have 6 there. So it does go all the way up to 4. So I do need 4 squared plus 1. Check and make sure that you have 6 rectangle areas. So I've got 1, 2, 3, 4, 5, and 6. Then when you crunch the numbers, you should get area based on the upper rectangles is about, I should say about, 27.875 units squared. Now we'll do the lower ones. Different color. Green. So the lower ones are going to be here. The lower ones start at 1. Still a width of a half. 1 squared plus 1 plus 1.5 squared plus 1 plus 2 squared plus 1 plus 2.5 squared plus 1 plus 3 squared plus 1 plus 3.5 squared plus 1. Ah, these green ones. The final rectangle, its height is based on 3.5. So you don't have 4 squared plus 1. And then you can check again. 1, 2, 3, 4, 5, 6. I've got 6 rectangular areas there. Crunch the numbers, and I'm getting that it is about 20.375 units squared. So this refines it. It's the same problem we did on the last time. So now we know that the actual area is between 27.875 at the upper end, and it's greater than 20.375 units squared. And then if we want to refine it even more, we can use even more rectangles, which is going to get really tedious. So there is a calculator program which I'll need to show you in class because my calculator here on the Promethean board doesn't have the program and I do not know how to get it on there. And you will need that program for your homework, so make sure that you get that on Monday. I'll show everybody. That's my plan on Monday. Okay, you might wonder if so like on this one, the upper area was based on, let's see, the upper one was based on the right hand, so that was the same as our RAM. And the lower one was based on, whoops, that's supposed to be A sub L. The lower one was based on the left hand X value for each rectangle, so LRAM. Is that always going to be the case? And the answer is no. And it depends on a certain attribute of the function. And maybe you can think about that and think about which type of functions, as long as they're increasing. So they can be increasing, but some increasing functions, the upper rectangles will actually be LRAM, and some will be RRAM. And if you can tell me, if you can think about that and tell me what you think, then let me know. Next. So let me catch up with my notes here. Okay, so that is A1. Now, A2 is the definite integral. See, this book scoots right along. It's giving you like a little crash course in calculus. A.2 is the definite integral. Okay, so let's draw the picture again. Let's draw the same curve. A to B, like I was saying. That's how we want to label those. And let's say we've got a whole bunch of rectangles in here that we're using. Think of these as little rectangles here that we're using to approximate the area under the curve. And the curve is going to be f of x. Well, the more rectangles we have, the closer the estimate will be to the actual. So you might have considered what's going to happen if the number of rectangles, n, so n we talked about earlier is the number of rectangles or the number of subintervals. What happens if n approaches infinity? Well, when that happens, as n approaches infinity, the estimate approaches the actual. So the way we could write that is, this is the limit, as n approaches infinity, of the summation of all of those rectangles, summation of the rectangles will equal the actual area. And we do have some notation for this, so let me show you that. X sub I is going to be a given x coordinate down here, and the corresponding height will be f of x sub I. So let's do this. We've got the limit as n approaches infinity. We're summing these, so we use the summation symbol, sigma. And we're summing the areas of the rectangles. I should have said sum of areas of rectangles. The areas of the rectangles are the width times the height. And I'm going to write it a certain way. I'm going to write the height times the width. So the height times the width. The height is f of x sub I. For a given, so x sub I would be like the x-coordinate of a given rectangle. And then when you plug that in to the function, you get the height of that particular rectangle. And then I'm going to multiply that. That's the height. And then the width is going to, we're going to call that delta x. And with sigma notation, we start with, in this case, I is my variable. So I will start at, I think it was 1. Yeah, from 1 to infinity, or to 1 to n. Okay, so that's the mathematical way of writing the limit of the sum of the rectangles. And then the actual area is an integral. And the way it's written is the integral from a to b of f of x dx. That is actually called the definite integral. So we can make a note of this. And these things have names. So the a is going to be the lower limit, because we're going from a to b. B is the upper limit. F of x is called the integrand. And x is the variable of integration. And what else was I going to say? Oh, and this symbol, this S, it used to be an S for in Leibniz and Newton. They were the pioneers of calculus. And they used, I guess that was the way they wrote their S's maybe. But it kind of evolved over time into the integral symbol. So that is a definite integral. That's how you write it. It means, and what it does is it tells us the actual area under the curve from a to b of f of x. Now our first example is to sketch, or maybe I should read what it says actually. Oh yeah, back on that slide, I'm going to go back a sec. Okay, good. So you have a picture there. You have the picture, you have the definition. Okay, so now example 1. Oh yeah, and then there's the historical note in the book that talks about Leibniz and Newton. Example 1, sketch the graph y equals x to the 4th over the interval 0 to 1. And then we're going to shade the area described by 0 to 1 of x to the 4th dx. So that's right, the integral from 0 to 1 of x to the 4th dx. Okay, so we'll do a sketch. And if you, y to the 4th is kind of like, it reminds me of a fencing staple, you know, like this. But if you zoom in on it, you can kind of, it does rise up off the x-axis a little bit there. Okay, so here's 0 to 1. And we're finding, this means we're finding the actual area here under the curve. And let me see what else. Oh, I think I might have got ahead of myself. Oh, shade the area described. So I just did that automatically without even thinking. Okay, so that was the requirement for letter A. Letter B, use technology to calculate the lower and upper rectangular sums. And so on that program that I have, it's in terms of RRAM and LRAM. It doesn't, that's the notation that they use. Whoops, That's supposed to say LRAM. So you have to figure out what that is in IB. And let's just do it. We'll just make, if you were to use 2 subintervals and you wanted the upper rectangles, that would be like so. Would that be RRAM or LRAM? Well, it's going to be RRAM because you're going to be using the right-hand side of the interval. So RRAM is going to give you the area using the upper rectangles. And then LRAM will be the lower ones. And actually, if you notice that with LRAM, if you only use 2 subintervals, you would actually only get 1 little rectangle here. So LRAM in this case is going to give you the lower estimate with the lower rectangles. Have you thought about when you would have an increasing function where these would be the other way? Well, I guess I'll tell you. How about one like that? Like a natural log, for instance. So you were going from A to B. If you divided it into 2 intervals, and if you wanted, ooh, that one's a little, yeah, never mind. If you used upper rectangles, you would actually be using the right-hand side. So RRAM would actually give you the area using the upper rectangles. Wait, did I do that right? Oh, wait a minute. So that's the same. Maybe you guys shouldn't listen to me. Upper. Oh, I thought it would be different. Well, maybe I'll have to think about that later rather than wasting your time. I'll think about that some more later. Obviously, I need to do that. Okay, well anyway, back to technology. So I'll show you that program on Monday, and then you can calculate when n is 5, 10, 50, 100, and 500, and then you will do A sub L and A sub U. So A sub U is going to be the RRAM on the program, and A sub L will be the LRAM. Okay. And then letter C is to actually, well, you have to use the program to get these values before you can do C. So we'll have to talk about that in class. Then example 2. Use graphical evidence and known area facts to find, letter A, the integral from 0 to 2 of 2x plus 1 dx. Okay, and then there's also a part B, but we'll do this one first. So we're using graphs and areas to do this. Well, let's graph it. It's a line, y-intercept at 1, slope of 2. Over 1, so it's going to go up there, and over another one up here. And I'm going from 0 to 2. So we're finding the area of that trapezoid. You have 2 choices on, well, at least 2. I mean, there's probably an infinite number of ways you could do this. But you could find the area of the trapezoid. Now, you are going to need to know that for future problems, so we could do it that way. Or you could subdivide this and do the area of this rectangle plus the area of the triangle, which would be fastest. But because you need to know the area of the trap, let's just do it that way. So it's 1/2 height times b1 plus b2. So 1/2. The height of the trapezoid is going to be 2. And then b1 is the first base, so we could call that one 1 here. And then the other one's going to be, what, 5? So 1 plus 5, 6 times 1, so 6 units squared. You could also do it, just to check, you could do the other one. So this is 2 times 1 is 2, and this triangle has a 2 by 4, so half of 8, which is 4. 4 plus 2 is 6. So either way, you're going to get the same answer. Then letter B is the same request, different equation, different integral. Integral from 0 to 1 of the square root of 1 minus, that's supposed to be x squared dx. Well, we have worked with this function a little bit before. Hopefully you will recognize it. If you don't recognize it now, after you do this example, hopefully you'll recognize it in the future. It is a semicircle. And when you graph it, well, I could show you where y. This is the y, so it's y equals 1 minus x squared. Well, the square root actually. And then if you square both sides, you get y squared equals 1 minus x squared. Add the x squared over. And then it's in a more familiar form, the standard equation of a circle. So then you can see that it's centered at the origin. It has a radius of 1 unit. So this semicircle here. It also we're only dealing with the top half because it's positive root. So we are finding the integral from 0 to 1 of this region, and so it's really just this part right here. It's just this quarter of a circle. And that's where the formula for the area of a circle kicks in. Pi r squared divided by 4 in this case. So we're going to have pi times the radius, which is 1 over 4, and so the answer is pi over 4. Now there is a way to do this problem by integrating, maybe. This one might be hard to integrate. Some functions are very difficult, if not practically impossible, to integrate. So sometimes you need to use geometry, like we did on this one, to actually get the answer. But we will learn how to do some of these algebraically. And that wraps up A2.